Thank you for the introduction, Jenny. And hello, everyone. It is my great pleasure today to present new structural motifs and the mechanism behind their formation that we detected in the complex and heterogeneous puzzle of Kraft Lignin structure. My supervisor here at KTH is Martin Awoko, and our industrial partner is Lorenzo. Our reference there is Dimitri. The structure of Kraft Lignin remains still today a topic of debate due to notorious heterogeneity. As a consequence of the main reaction occurring during pulping and also the Kraft process itself, Kraft Lignin structure can be defined as a result of cleavage and repolymerization of lignin fragments. This leads to structural heterogeneity, but also heterogeneity in terms of chemical functionality, as well as molecular weight, polydispersity. Here we can see, for example, that we have a lot of different functional groups like carboxylic, we have aliphatic, and we have also different molecular weight. This is a problem, it's a hurdle that is needed to tackle, especially when the target is to investigate the authenticity of some of the mechanisms that happens during the Kraft process, which it's not well understood in terms of structural chemical of lignin. To solve this problem, in 2017, Christine and co-workers, this is one of the main approach, fractionated lignin with acetone, and they came up with this model which well summarized how heterogeneous is lignin. We can see that here on the left, we have native more native linkages like beta-4, like phenylcumaran, like resinol structure. This fraction is the acetone in solvent fraction, which has been shown to be more linear and more polymeric. On the other hand, in the same structure of Kraft Lignin, we can see that we have abundance of enoliter, stevin, vanillin, which are Kraft-derived units, which are found in the acetone solvent fraction. This fraction, it's more branched and it's definitely has a lower molecular weight. Our approach is different. We profile the structure of spruce in this work and eucalyptus lignin after sequential solvent fractionation. The refining was achieved by a carefully designed sequence by our group of green and sustainable solvents like ethyl acetate, ethanol, methanol, and acetone. Second data shows that fractionation of Kraft Lignin in terms of molar mass was achieved for both spruce fraction and eucalyptus fraction here shown. Here we can see that the dispersity of the isolated fraction, which is represented, the fraction with different colors, as we can see here, it's definitely lower than the pristine, the starting material is in the dotted line. This low dispersity is a condition sine qua non if we want to make material, if we want to make new polymers from lignin. The content of functional group of the isolated fraction was calculated by phosphor NMR. Here we show only the result for spruce fraction, but we got exactly the same trend for eucalyptus fraction. Here we can see the higher molecular weight fraction, so the acetone and the resin, that we have a low phenolic content, it's the blue line, but also we have a high content, it's the orange line. And according to HSQC analysis, this fraction here are abundant of native lignin subunits, a little bit what Christine, we have shown before with Christine's work. Here, in this high molecular weight fraction, the molecules have a low aromatic density. This density is low because the aromatic units are coupled to each other by the propane side chain. So like with the native linkages or like beta-4, phenylcumaran. But on the other hand, the lower molecular weight fraction, and especially the ethyl acetate here represented, we can see that we have a peak in the phenolic content, and it's devoid of aliphatic. This means that here the molecules have a oppositely to before high aromatic density. The aromatic rings are seems to be directly coupled. This high aromatic structural density, we thought that can be the consequence of retroaldehyde reaction, which leads to formation of guaiacol. And thereafter we have radical coupling to produce highly condensed lignin structure. This hypothesis was proved to be true in our first work on softwood Kraft Lignin, where for the first time ever, we provide clear evidence of a new direct carbon-carbon linkage between the aromatic units. And it's 1,1, here we can see circle, and 1,5, again in the blue circle. The fact that at least one carbon-1 is involved in the linkage, this support that retroaldo occurs, and after we have radical coupling. Our modus operandi involved advanced NMR analysis of the model compound, which we synthesize ad hoc. In the case of Spruce study, we started with Guaiacol. Thereafter, we combine the study of model compound and we compare this with the structural study of the refined lignin fraction. And our data show that when Guaiacol polymerize, we only get favorable carbon-carbon, like the structure in red, linkage, and over rather than the structure containing the ether bridges. Oops, something has happened here. Is that fine? Okay, yeah, sorry. I got some. With the same aim, we adopted a similar strategy using different composition of the monomeric substrates to study now the structure of eucalyptus Kraft Lignin, which is the focus main of this presentation for matter of time. Also, when Syringol polymerized or Syringol in presence of Guaiacol, we got, according to NMR characterization, the presence of only structure with carbon-carbon direct linkage. But let's see how we got this information. I'm sorry, but sometimes it gets stuck here. I don't know why. Can you see or? Hello?
Yes, we can still see.
Yeah.
That's good.
I don't know. Yeah. Okay, so how we got this information? Here we can see an overlay of HSQC spectrum of the starting monomer, the Syringol in black, whose peak are represented in black, with its oligomeric product, the SS model compound. So when we polymerize Syringol, here we could detect this peak, cross peak, which we have assigned to the protonated carbon in position 2,6 in the symmetric 1,1 tetramethyl diphenol, which I've drawn here in red, we can call S11. Analysis was confirmed by HMBC. HMBC is a very powerful tool which allows us to identify atom connectivity up to 3 bonds and also between 2 different spin systems. And here we can see the alignment of the protonated carbon in position 2,6 with the 3 non-protonated carbon. The only way that we can get this atom connectivity, it's an asymmetric 1,1 para structure. In addition, I don't know, we previously, in addition, we have detected for the first time a cross-peak proton-carbon correlation at a high proton field, which has been assigned in at protonated carbon position 2,6 of the para-benzoquinone. Again, the assignment has been confirmed by HMBC, where we can see the alignment with the 2 conjugated carbonyl in position 1 and 4, which they come up in the ketone region. Then we studied the SG model system, which were mixed in ratio 2:1 to recreate the hardwood monolinear composition. In this case, the key observation came from the HSQC toxic analysis, which we showed the lack of any peak related to carbon-1. Together with the presence of the diagnostic peak that we previously have discussed, the detect of S11, we could also see the HSQC toxic correlation between carbon-2, carbon-5, and carbon-6 in the Guaiacol region. Again, this supports the presence of 2 Guaiacol units that couple in para position, forming the 1,1. The main lignin structure, interunit linkages, and the end group of the fractionated lignins were studied by depth-edit HSQC and quantified by carbon NMR. The beauty of depth-edit HSQC is that we can distinguish the methyl group from the methylene group because they have different phase, so opposite phase, we got different color. The take-home message of this slide that if we sum up the contribution to the total linear linkage from the aliphatic side chain coupling, we can see that we don't get not more than 50%. Where do end up all the linear interunit linkage? Well, it's in the aromatic. One of the hypotheses that this suggests that most of the aromatic interunit linkage comes here in the aromatic region, which is the focus of this study, here in the reference also of the well-characterized model study that we have just presented. So what we did, we overlaid the HSQC aromatic region of Kraft Lignin with the two model compounds that we just presented, SS model compound indicative of S11 and SG model compound indicative of 2G11, and we can already see by visual inspection that we have an overlay between the Kraft Lignin cross-peak and the model compound. Or again, HMBC analysis support the study, showing the same atom connectivity in the found in the model compound system. One of the very interesting outcome is that also Guaiacol units in hardwood lignin, like in this case, undergo retroaldo and radical coupling. Turning to number, we have roughly 10% in eucalyptus Kraft Lignin of linkage where at least one carbon 1 is involved. This percentage is much higher in ethyl acetate fraction. And this is not surprising because we have seen that according to phosphor NMR result, this oligomeric fraction has a high phenolic content, it's low, it's devoid of aliphatic. This fraction, in our point of view, it's very attractive in a material context. So to sum up, we identify unequivocally the presence of 1,1, 1,5 interunit linkages and the 3,5-dimethoxybenzoquinone in Kraft Lignin. These structures are signatory of retroaldo followed by radical coupling reaction, and this seems to be a key reaction in the reconstituted fraction of Kraft Lignin. This happens because a new accessible radical condensation spot is created in carbon 1 position in the form Syringol and Guaiacol, where such condensation occur without any discrimination. Quantitation of this structure is similar for spruce and eucalyptus, and we are roughly at 10% of all interunit linkages. Last but not least, I would like to thank the founding, so the platform Treesearch, which has been founded by Program B Innovation, Vinova, and indeed the industrial partners, and so with the person of our content, Dimitri Areskor, which is my supervisor, and my boss here, my supervisor here at KTH, Professor Martin Labo.